Hello, everybody. Yet another recorded Zoom interview, this time with Dr. Jamie MacDonald from Florida Gulf Coast University, way on the other side of the country. What is the weather report today there, Jamie?
Oh, I think it's in the 80s. I think it's 87.
Oh my God. Wow. Okay.
Well,
Well, we,
the low is in the 60s this morning, 68 or something. The humidity's only in the 80s though.
geez. Well, it's the end of a long Thursday for you in the classroom, and I appreciate your time here. Let's go right into it, Jamie. I want to talk about the Western Melange Belt and potentially following it south to the Rimrock Lake Inlier, because I think you're aware that I'm trying to think hard about the basement south of Interstate 90 and learning what I can. And you've gotten all sorts of experience with that. Can we start with how did you get interested in doing field work in the Central Cascades?
I'm a little long-winded, as Nick knows, and
Go
so
for it.
I apologize. This might be the only thing we you get to. My graduate advisor, Greg Harper, who now lives in the suburbs of Vancouver, Washington. He's retired and he loves it there. Um,
Mhm.
Greg is I talk about Greg in the past tense. He's fine. He lives in the suburbs of Vancouver, Washington.
Okay.
Greg was probably one of the most eminent Ophiolite scholars in the world, and he was Mr. Josephine Ophiolite. And I say that in a nice way. The Josephine Ophiolite is a Jurassic Ophiolite that's in the Klamath Mountains, so Northern California, Southern Oregon, near the coast. The Josephine Ophiolite is very well preserved. You have a remnant arc, so the arc that was active before the basin opened, called the Woolly Creek Batholith. You have the remnant arc that's built on older accreted terrains in the Klamath Mountains in Northern California, Southern Oregon. You have the Rogue Chetco arc, which is the active arc above the subduction zone, which is the outboard arc. The subduction was to the east underneath North America. And
Okay.
so this is the active Jurassic arc rocks, the volcanoes that sit above the subduction zone. The ocean basin that opened up in between them was the Josephine Ophiolite, and then the Gliese Formation deposited on top of this, and then the whole thing closes during the Nevada orogeny, right?
Good. I'm with you so far.
Greg was a Jurassic guy. He liked Jurassic tectonics. He liked ophiolites. Bob Miller, who wrote his PhD thesis on the Ingalls ophiolite, only the best people do. Bob Miller wrote his PhD thesis on the Ingalls ophiolite, and he wanted to collaborate with Greg Harper on doing a modern study on the age and the geochemistry and the structure of the Ingalls ophiolite. So I went to graduate school, and my advisor was so kind to me, which was I did not deserve it. And he would say things like, "Oh, well, Jamie, you're going to work on the grant." And I'd say, "Okay." And so the grant, well, he had a couple, but the grant was for the Ingalls ophiolite. So he said, "You're going to go out, I wanted to work on ophiolites." And so he says, "You're going to go out, you're going to work on the Ingalls ophiolite." And Greg Harper was working on the Ingalls ophiolite because it's a Jurassic ophiolite in the North American Cordilleran. And the age was originally 155. That was published in Miller et al. 1993. Um, that Bob might have talked to you about or may talk to you about. And then,
Hmm.
so we want to do modern geochemistry, modern age dating, and modern structure because the age was a Cliff Hobson, Jim Matson age from the 1970s. And the age was 155, but the lead age was in the 166-ish age. So when you do the uranium lead isotopic ages, you get three ages. You get two uranium lead ages, you get a lead age. And they all should be the same age. That's why it's called concordia, right? And if the lead age is wrong, you're losing lead. Lead is the one thing that can leak out in the uranium lead isotopic system. And so, okay, we know the ages might be off because the lead. So I started working on the Jurassic Ingalls ophiolite. We found out that the real age was closer to 160, 161. I also found, really Bob found it, but I studied it in detail. We worked on, Bob Miller found it. We worked on the basement rocks, or these older, weird ophiolitic rocks that are in the Ingalls ophiolite that are early Jurassic. They're in the 190s, 192-ish. So there's these early Jurassic and then late Jurassic ages in the Ingalls. So Ingalls is a polygenetic ophiolite, and that's just fancy talk for it's made up of more than one piece of oceanic crust. So all right, I do my PhD thesis on the Ingalls ophiolite. I publish papers on the Ingalls ophiolite. In Bob's 1993 paper, he says incorrectly that the arc rocks in the Washington Cascades are probably the Rogue Checo arc because they're basically the same age. Rogue Checo arcs in the mid 150s to late 150s. I'm sorry, mid 150s to early 150s.
Mm-hmm.
The Hicks Butte complex is 153. The Quartz Mountain stock is 157. And the Indian Creek complex in the Rimrock Lake Inlier is 150. I know this, hold on. It's 154,
Okay.
right? So, okay, these are probably the same rocks. And when I was doing my dissertation, the age, the geochemistry, the sedimentary rocks that sit on top of them are so similar that we said that the Ingalls ophiolite is correlative with the Josephine ophiolite. And so they're not necessarily in the same oceanic basin, but they were in similar oceanic basins occurring at the same time next to each other. Because the paleontologist, his name's Emile Pisano, who did the radiolarian from chert ages for us, said the chert assemblages in the sedimentary rocks that sit on top of the Josephine ophiolite are identical to the chert assemblages that sit on top of the Ingalls ophiolite. So okay, their ages are almost the same. Their geochemistry is basically the same. Their sedimentary rocks are correlative. So we got these very similar ophiolites occurring, very similar pieces of oceanic lithosphere occurring near each other. One, the Ingalls, has just been translated to the north, like all Washington terrains, right? So then, if these other arc rocks are supposed to be the Rogue Checo, let me go look at those. It turns out they're not.
Mm.
but um, but so I started working in the Menashe Tash Inlier on the
Good.
Quartz Mountain stock first. And that was also part of my dissertation. And the reason why I went to the Menashe Tash Inlier to work on the Quartz Mountain stock first is because the lead age in the Quartz Mountain stock was in the 160s, just like the Ingalls ophiolite. So we thought, oh, maybe this age is wrong also. It wasn't. I got the same age that Jim Matson got in the 70s. So I also got 157. Then after I finished working in the Quartz Mountain stock and then the Menashe Tash area, although you never really finished, right? I just naturally went over to the Hicks Butte and
Good.
started working in the Hicks Butte Inlier. And the Hicks Butte age was the only one that wasn't discordant. It was 153, 153, 153. It was almost perfect. The two uranium lead ages and the lead age were always the same 153. The reason why, this is kind of funny, I went into the Hicks Butte complex is I had money. You've been up to the Menashe Tash Inlier. There's
Yeah.
some amphibolites called, and I named them the Hereford Meadow amphibolites after the Hereford Meadow. There's these weird orthogneisses, these very light colored leucocratic, right? These felsic gneisses, very fine grained, that are in with the amphibolites. They're weird. And I wanted to get an age in them without going into too many details. So I had money, so I collected a bunch of sample and I sent them to the very well regarded LaserCon lab at the University of Arizona. Even though I collected a sample that had really high zirconium and was very felsic, I thought this is a perfect sample to have crystallized zircon out of the magma. Zero zircons.
Ah,
So Mark Pekka, who is the nicest man, felt bad for me. And Mark said, listen, these two samples you sent me have zero zircons in them. Send me two other samples and I'll date them. So I said, what else do I got? Well, I have a couple of things from the Hicks Butte. I'll send him some Hicks Butte samples. So then I sent him the Hicks Butte samples. and I sent him a tonalite, and I found these weird dacite that no one had ever seen before. People just missed them in the Hicks Butte complex, and they're very pretty. Once you see them, you're like, oh, how did I miss these? And then things really started getting interesting because those dacites were Cretaceous. They were
Okay.
104 million years old. There's nothing else in the state of Washington that has an igneous age of 144 million years old. And the dacites have this weird chemistry called adakite. You might have heard of adakites with Tepper.
Yeah.
Adakites can form in all sorts of different places. These adakites look like they formed from the melting of mafic crust, and they did. And so after hooking up with Peter Davis from Pacific Lutheran University, and we worked collaboratively on the Higgs Butte for a few years now, we have discovered that there's gabbro in the Higgs Butte that's symplectic. Symplectic's fancy term for it melted. It has it has preserved textures in it that show that it was melting. And the adakite, these funny dacites that form from the melting of mafic crust that are 144 million years old have remnant zircons in them that are in the 150s, 153,
Huh.
the age of the Higgs Butte complex. And
There we
so,
go.
and if you partially melt the gabbro, you can make the dacite. So that was very long-winded. I
No,
started
that's
studying in the Higgs Butte because it was supposed to be the equivalent to these arc rocks that are in Northern California, Southern Oregon. They're very different. They're
very different.
very interesting, and they don't seem like they're related at all. And
Well,
really,
I'll tell you
that,
what. Look,
you get a hodgepodge of Mesozoic terrains in Washington State, and that's gonna. And so, go ahead, ask your next question.
well, let's go ahead. Can we go to a slide that
Oh,
shows the locations of those little inliers, those little postage stamps that you were just talking about, to give our viewers a feeling for how this might connect to the Bob Miller discussion that I had about an hour ago, by the way. And we were talking mostly about the Rimrock Inlier and also
yeah.
about the Western Melange Belt. So this is a good way to just get us in. And I love this map for many reasons, Jamie, including you are making a stab on where to bring the Straight Creek Fault south
Oh,
of Interstate 90.
I
And
got
I
a
don't know
little
how.
brave, didn't I?
Yeah.
Now,
So yeah, please go ahead.
here's the Ingalls ophiolite.
Thank you.
Can see my pointer okay?
I can.
I'm gonna do this instead. Oh, I'm not in presentation mode.
Oh, you're great.
If I do this, am I still sharing the right screen?
Yes. Razzle dazzle. Look at
There we go.
this. Yeah,
Here,
perfect.
here is the Ingalls ophiolite,
Thank you.
crusted over the Cascade crystalline core.
Yep.
So this is the first in the Central Cascades. This is probably the first terrain to arrive, and its thrusting is synchronous with the formation of the Mount Stewart batholith. It's about the same age. The Windy
Mm-hmm.
Pass thrust is about the same age as the Mount Stewart batholith. Then here's the Catchise Lake inliers, which are mostly Eastern Metamorphic Suite. Then just to the southwest is the Hicks Butte inlier, which the Hicks Butte complex is within. And then just to the south of the Hicks Butte inlier is the Menashtash inlier. Inlier means you have older rocks that are surrounded by younger rocks.
Mm-hmm.
And so these are Mesozoic rocks that are surrounded by Cretaceous rocks. And then down to the southwest, even more, is the Rimrock Lake inlier. The Straight Creek Fraser River Fault. See, there's no geology north of the 49th parallel, right? And so,
Of
oh,
course,
yeah,
right.
yeah. So we don't have the Canadian geology there. But the Straight Creek Fraser River Fault comes down from the border. It's north of the border, and comes down here, and then it does something funny. It starts to the fault starts to deflect to the southeast when you get into these inliers,
Mm-hmm.
which is very interesting. Megan Anderson maybe has an idea about what possibly is going on there, but you very clearly see these faults start to deflect.
Okay.
Uh, this fault right here has a name. It's called the Tanum Creek Fault Zone.
Mm-hmm.
On the opposite side of this fault is the tectonic complex of Stout, which is a terrible name, but it's really just the hell in a haystack melange. And so you can match it back up over here with the hell in a haystack melange. And so therefore, this fault right here is essentially the Darrington Devil's Mountain fault zone. And so you can actually use this fault as a piercing point along the Straight Creek Fraser River Fault.
So what's the argument against continuing the Straight Creek Fraser River Fault straight south as you dash there?
So the reason why I've dashed it is because you can't see it.
Yeah.
And so since you can't see it, you're really not sure if it's there. I dashed it down as far as I did because the rocks in the Rim Rock Lake Inlier, the Russell Ranch complex, the sedimentary rocks that are now deformed into a sedimentary melange,
Yep.
are correlated with the rocks in the Western Melange Belt. I purposely made them the same purple, right?
Yes.
And so if these rocks are really the same, possibly the Western Melange Belt just continues in some disjuncted fashion, some disrupted fashion, all the way down to here. Western Melange Belt is on the west side of the Straight Creek Fraser River Fault. And
Yeah.
so kind of sort of made it go down to there to keep it on the west side of the. Also, these faults that run through the Rimrock Lake Inlier have a north-south orientation, oh, just like the Straight Creek Fraser River Fault, right? And these faults in the Rimrock Lake Inlier are the faults that are separating the Russell Ranch complex, the sedimentary rocks, from the Indian Creek complex, which are the Jurassic Arc rocks. And so
So, so what would prevent us from continuing that purple even south of the Rimrock Lake Inlier? If we want to just be as simple as possible, why couldn't we just keep the Straight Creek River Fault heading south and just following that Western Melange Belt stuff all the way to Oregon? Is there any reasonable way to do that?
there's not because there's no rocks in Oregon and the subsurface that look like the Western Melange Belt. There's just no
Yeah.
data to allow
Yeah.
that to happen. And,
Yeah.
and I'm very fascinated with what is below the rocks that I find troublesome because they
Yeah.
open. What is below the Columbia River basalt? What is below all these younger volcanic deposits? What are
Mhm.
where are the interesting rocks, right? Where's the basement? The basement in Washington State is a series of accreted terrains. Your famous fruitcake, right?
Right.
That are all smooshed together by faulting. They started to assemble sometime in the Cretaceous, and they continued to assemble sometime after 74 million years
Mm.
ago. And when did they stop? I don't know. I'm not sure. But sometime after 74 and before the Straight Creek Fraser River Fault starts moving.
Can
Um,
we talk more about the Western Melange Belt before we go back to a couple
Absolutely.
more slides?
Absolutely.
Um, I'm imagining, and I did this with Bob an hour ago, I'm imagining for the Western Melange Belt a bunch of stuff in a blender. I have a bunch of Arcosic sand, and I've got big blocks in the blender of gabbro and chert and limestone and other things. What have you found in the Western Melange Belt that is new information compared to Bob's work back in the 80s and 90s? Have you been studying some of that sand in the Western Melange Belt?
Yes, but this was part of a large mapping project with Joe Dragovich. Joe Dragovich used to work for the DNR, Department of Natural Resources, for the state of Washington. Um, and part of the state map program, this is the federal funding to make geologic maps. We were going to map the Puget Lowlands because they were poorly understood. And we were really focusing on active and potentially active faults because large number of people started migrating to the east from Seattle metropolitan area. They were moving into farmland that it really didn't matter when there was one or two farms that if there was an earthquake. But now there's a lot of people moving into this area. and it's landslide prone, as like the Oso landslide was very famous, recent landslide, and it's earthquake prone. There are earthquakes all over the place, and they really had no good idea what faults were there, what were their orientations, how did some of the major faults like the Swift, the Southern Weeby Island fault,
Mm.
or the Seattle fault, how do these things sort of, because they're all kind of meeting in this area, right? And so we started in the Snoqualmie 7.5 minute quadrangle, then did Carnation, then Monroe, then Lake Joy, then Sultan, then Lake Chaplin, then Lake Rosinger, then the Granite Falls, where you were with Jeff,
Yeah.
absolutely mesmerized by Mafic enclaves. I had no idea somebody could like Mafic enclaves that much. Just to put a bow on the Mafic enclaves, your president of your university, Jim Wolpart, his wife is an eminently talented person because she's a geologist. And she used to teach geology at Florida Gulf Coast University with me, unfortunately for her. And she used to bring in a granitic sample to show students a xenolith. And
Mm.
she was very proud of her xenolith. And one day she says, "Oh, do you want to see my xenolith?" I said, "I would love to see your xenolith." And she shows it to me, and I said, "That's a mafic enclave." She had no idea what a mafic enclave was.
Most of us didn't at the
And she didn't
time. Yeah.
understand that magma mixing and things. I said, "Well, it's still very interesting because it represents magma." Anyway, so
Love
our
it.
last one was Granite Falls. If you look at the Granite Falls quadrangle, we
Yeah.
purposely Joe Dragovich purposely wrote that quadrangle as a synthesis of all these other quadrangles. So
Okay.
we started working in the Western Melange Belt in the Snoqualmie area. I'm telling you the story with purpose, I swear. In the Snoqualmie area, it looks like a melange. It's got a scaly, disrupted sedimentary, fine-grained sedimentary rock fabric with pieces of stuff in it, right? But as we moved from the south towards the north, it changed.
Mm.
Instead of looking like the Russell Ranch complex in the Rimrock Lake Inlier, it
Thank
started to
you.
become very different. It started to become, instead of a scaly matrix melange, it started to become large coherent blocks on sort of a hill or small mountain scale that were
Yeah.
intact within that block. But as you went from one sort of hill or mountain to the next one, the lithologies would change, the metamorphic grade would change, things would change. So it went from a mesoscale melange to a very large scale melange, right? It went from,
Interesting.
yeah. And so, and one of the Western Melange Belt exists in name because when Frizzell and Roland Tabor, when those guys came through to map that area, those magnificent large quadrangles they did, there were dozens of little tiny units that were generated from numerous master's and PhD theses out of University of Washington. And they had all sorts of different names. I have some of the names here, like the Old Metamorphic series, and the Olo Mountain units, and the Sultan units, and the Stiligamish group, and the Woods Creek intrusive bodies, right? And so they were all over the place. There was lots of little units. They're all kind of sort of the same age. They were all sort of the same metamorphic grade. They're lithological, so they got lumped. They got lumped into two melange belts, one called the Western Melange Belt and one called the Eastern Melange Belt, where the Eastern Melange Belt has slightly older ages and a slightly different metamorphic grade, and it has more serpentinite in it. It has more
Mm.
ultramafic rocks in it.
Hmm.
So the Western Melange Belt goes from things that look like the Rim Rock Lake to things that look very different. But um, we kept doing this a very similar study where we would do geochemistry and petrography and age dating of the metasedimentary rocks and the metaigneous rocks through the Western Melange Belt.
And so you're comfortable lumping uh, Rimrock with Western Melange. It sounds like you colored it the same lavender color.
If I had 30 or 40 more years, yeah, I'm only 50. If I had 30 or 40 more years, I might unlump large portions of the Western Melange Belt
Oh, interesting.
because the units become very coherent as you head off towards the north.
Okay.
Let me hold on one
Yeah,
second.
yeah, let's go back there.
I have a map that I'd like to show. It's too busy. I'll
Okay.
show it very quickly though, and I'll talk about it in a very simple way.
Thank you.
So this is a map of the Western Melange Belt.
Mm-hmm.
And down here, we have Metagabbro and metavolcanics and metasedimentary rocks. And we can very clearly see the contact between them. We can see relic igneous structures like pillows from pillow basalts. We see beautiful graded bedding, beautiful rip-up clasts. They're very weakly deformed. This is
Mm-hmm.
the Blue Mountain area, um, which is over in the Puget Lowlands. When we jump to the next hill, we go from low grade metamorphic rocks to much higher grade phyllites.
Huh.
So we're still in the Western Melange Belt, but all of a sudden we went from things that were sedimentary rocks where you could really clearly see the original sedimentary structures to things that are more penetratively deformed and deformed at a much higher temperature. And so as we were going from mountain to mountain to mountain, from hillside to hillside, the metamorphic grade would change, the lithologies would not change, but just the way they were interacting you could, in one block, you'd have really nice contacts, and the next block, everyone's faulted next to each other. So there were a lot of really interesting and significant differences.
So
So,
that's a crazy quilt right there, or
yeah,
fruitcake.
right.
And I'm trying to
Without
visualize.
fruitcake.
Yeah, I'm trying to visualize the basement south of I-90, and you're saying a potential option is it's that complicated on that scale. That could be the look of the basement.
Because,
Uh,
well, just when you think of the Mesozoic terrains,
yeah,
you think of the Northwest Cascade system. You have all these
right,
things mixed together. Eastern
right,
Metamorphic Belt, the Bell's Pass Melange, the Chilliwack, the Yellow Aster Complex, the Twin Sisters Dunite. And then you
yeah.
go to the San Juans and you have all these different things mixed together that are different than what's in the Northwest Cascades. And then you
Mm.
go to the Central Cascades where you have rocks of similar age. They're broadly similar, but again, different. Ingalls is different than the Eastern because it's much lower metamorphic grade. The Hicks Butte complex looks like things that are in with the Northwest Cascades, but it's a much lower metamorphic grade. So if you just go east to west, along the Cascades towards the San Juan Islands, you have this huge hodgepodge. So you could just take that same hodgepodge and just place it down there to the south and have this varying amounts of terrains that are all sort of mixed together, making up the basement below the younger rocks that are sitting on top of them, that these ancestral cascades and modern cascades are building through.
Well, this is great. You're doing a great job. Let me throw a hypothetical at you, Jamie, and then we can go back to a few more of your slides before
Sure.
we quit here. This is great. Um, if I am a magma 3.2 million years ago, and I am ascending through the crust at the goat, what is now known as Goat Rocks.
Yeah.
And I am just at the very beginning of starting this Goat Rocks volcanic complex. I'm imagining at the simple end of the spectrum, the basement is just a bunch of Russell Ranch. And it's easy to just say just a bunch of Russell Ranch, but I'm imagining just this Arcosic sandstone with a few little blocks here and there. But the other end of the spectrum is I'm this Goat Rocks magma that's coming up through this virgin crust, and it's just as complicated as what you just said.
It could
Do you
be.
have any hunch, one, the simple versus complicated? Is there any way to get a sense of what that real estate might have looked like 3.5 million years ago?
Well, because the Rimrock Lake is proximal, it can't be that different. And
Hmm.
so, but you also have things like Indian Creek Complex in there. So,
Yeah.
and the Rimrock Lake Inlier is mostly made up of rocks that are going to have a melting temperature that are higher than the melting temperatures that are making up the intermediate to felsic magmas that make up these ancestral and modern cascades.
Hmm.
One of the things, this is a long way to answer your question, but it's me.
This
I
is great.
apologize.
No, go.
Well, I've worked a little bit with Rosemary Hickey Vargas in the Andes Mountains, and one of the things they think about constantly down there is how did the basement affect the chemistry of these magmas that are erupting in these modern volcanoes?
Okay.
And they have all these different techniques to see was there garnet down there, was there amphibole down there, what was assimilating, how was any kind of assimilation melting into the magma, affecting the magma's composition. Ignorantly, I don't pay very much attention to the people who study the modern cascades. But when I do hear talks, I never really hear them talking about things like assimilation or any crust getting entrained. You know, when they have zircons, they don't ever really have old zircons when they date them out of these modern magmas.
Hmm.
Um, and you don't see xenoliths of things that look really old. You normally just see xenoliths of older igneous rocks that are really not that much older than the volcano because they're just, maybe, a few hundreds of thousands or a million or 2 years older, meaning they're from the same magmatic system.
Hmm.
So I
Hmm.
always found it interesting that people who work in the Andes think all the time about the basement, but I'm ignorant about the people who work in the modern Cascades. People who work in the modern Cascades, the volcanoes, I don't recall hearing them talk about how the basement might affect the magmas. And so when this felsic to intermediate magma is coming up, if it's coming up through green schists that used to be basalts and very dense argillites, it might not have a lot of assimilation going on. It's probably hard for it to incorporate that stuff into it. Plus, those rocks are so faulted. This is more of a Bob Miller question, but those
Uh,
rocks are so faulted, it might be easy to kind of push all that rock out of the way instead of just sort of assimilating
uh,
it.
yeah.
But interesting, you have things like the Indian Creek Complex, which are intermediate to felsic rocks. So there might be a bit of a mixing there. I've looked at some. I'm since I've never worked in Rimrock Lake Inlier, but I'm interested in it. Because it is correlated with the Western Melange Belt. It's correlated because the radiolarian ages are the same. It's correlated because the lithologies are the same. The rock types are the same. It's correlated because it has an arcosic sandstone, and one of the sands there's really three different kinds of sandstone in the Western Melange Belt, and one of the major three types is also arcosic,
Huh.
and petrographically looks exactly like the sandstones in the Rimrock Lake
Rimrock.
Rimrock Lake Inlier.
Yeah.
And there's Permian limestone blocks in the Western Melange Belt. There are Permian limestone clasts and
Yeah.
breccias in the Rimrock Lake Inlier, the Russell Ranch complex. So we have all these affinities that are very similar. And there's greenstone blocks in both, although the geochemistry of the Russell Ranch complex in the Rimrock Lake Inlier, it's not too many R's, hard to alliterate, is it hasn't been modern geochemistry. There's just a master's thesis done in the 80s. And
Yeah.
he only did X-ray fluorescence. So he only has some elements, not all the
Hmm.
fancy trace elements that people like to use. So broadly speaking, we know a little bit about the the chemistry and where those rocks in the Rimrock Lake Inlier might have come from. But broadly speaking, they're kind of the same chemistry as the ones in the Western Melange Belt. So there's all these lithologic similarities. Um, and uh, and so this is why they get correlated with each other. And so as the magmas are coming up, either they're structurally weak because it's a melange, so it might be easy to sort of push them out of the way, and
Yeah.
they might have different melting temperatures, and so it might be hard to assimilate them. But these are questions that igneous petrologist who studies magma chambers of volcanoes would be better suited to answer. So I don't know. And so I've look at some papers like Paul Hammond's papers. When Paul would work in that area, he would sneak into the Rimrock Lake sometimes and grab a sample or two and do geochemistry. So I know I look at some of the modern papers because every once in a while, someone who's smart, like Paul Hammond, grabs a sample of the basement down there and says, I'm going to do this and see if there's any similarities. And there never really seems to be. Maybe that's why they ignore the basement.
Thank you. Couple more. What is the youngest material that you have currently in the Western Melange belt? And is that important to figure out what the youngest stuff is?
It's important for a number of reasons. The youngest thing in the Western Melange belt. Well, let's look at the youngest and the oldest.
Okay.
'Cause they're both detrital grains of the mineral zircon, which is a zirconium silicate.
Okay.
So I'm going to show a slide real quick. I
Thank
promise.
you.
Be quick. You're welcome. I don't do anything quick besides talk. The youngest thing. So these are very complicated for people who aren't aware of what they are. I apologize. But the youngest thing in the Western Melange Belt, to my knowledge, is this detrital zircon age that's 74 million years old. It's
Okay.
getting towards the end of the Cretaceous. How close to the end of the Cretaceous is it? It's getting very close to the end of the Cretaceous, very late Cretaceous.
Yep.
This is important because the ages of the sedimentary rocks are used to study the thrusting that occurs within the Northwest Cascade system. And so when Ned Brown wrote this paper trying to bracket the ages of the assemblage, the thrust faulting that formed the Northwest Cascade system, Ned's age was in the 80s. So Ned said that, oh, well, the youngest thrust fault must be in the 80s.
Mm-hmm.
So he says, okay, this thrust stack down here is this old, this thrust stack down here is that old, and then this thrust stack on the top is the youngest, but it's in the 80s. We now know it's at a minimum, a maximum, it's 74 million years, and so the thrusting occurred sometime after that. So it's important to know that to learn the age of the assemblage of the Northwest Cascades when you had these trains coming down from the south and placing themselves as thrust faults up to the north. We used to think that happened in the 90s, 90 million years ago, plus or minus, like the Windy Pass thrust and the Ingalls
Yeah.
ophiolite over the Cascade crystalline core. Then we started getting more information in the Northwest Cascade system. This is the Royal We. But then Joe Dragovich, Kirsten Sauer, and myself, all of us who were working together, we got this 74 million year old age detrital age out of this Arcosic sandstone. It's Arcosic, just like the Rimrock Lake Inlier. And so therefore the thrust sheets that make up the Northwest Cascade system could be much younger. They could
Mm.
sneak into the Cenozoic if we're not
Right.
careful, right? Then the oldest mineral we found out of the Western Melange Belt is possibly the oldest zircon ever found in Washington State. In a lithic facies sandstone. So this sandstone has a lot of, it's not arcosic, it's lithic. It has a lot of volcaniclastic rocks in it. We have a 3.3 billion year old zircon that must be coming from the Canadian Shield and a detrital sedimentary rock that's Cretaceous in age.
Wow.
To my knowledge, this might be the oldest thing in Washington State that anyone has found so far.
Where was that collected?
This sample's from Willard Quarry. Joe Dragovich was doing some consulting work recently, and it's somewhere by Sultan, I think. Joe
Okay.
better, but he was doing some consulting work, and he just grabbed the sandstone because we needed a few more ages. Because we have this stratigraphy that we've been working out, the structural stratigraphy that we've been working out in the Western Melange Belt, where it looks like the in a very classic thrust setting that we have older rocks, these Jurassic sedimentary rocks thrust on top of Jurassic um, meta-igneous rocks that are thrusted on top of Cretaceous sedimentary rocks.
Yeah.
And so we were trying to grab a few more sandstones to help bracket this thrust stacking. So within the Northwest Cascade thrust system, we have thrusts within thrusts.
Right.
So we have these little thrust stacks inside of a larger thrust sheet that's thrusted up over the rest of the Northwest Cascade system. But we're getting very far removed from the Rimrock Lake Inlier. But so the youngest age is in the 70s. They're Cretaceous. The Arcosic sandstones are Cretaceous. There are a lot of Cretaceous chert ages, just like in the Rimrock Lake Inlier. So if you did detrital zircon work like Mike Eddy does, down in the Rimrock Lake Inlier, the sandstones are very similar to these Arcosic sandstones petrographically, meaning they're made up of the same little broken pieces of sand, or at least similar compositionally. They might also be in the 80s and 90s and maybe in the 70s too.
This is great. I got one more, and then you can add anything you want to do after that, Jamie. But it's after quitting time for you. Come on, man. It's after 5 o'clock. Um, so you were just describing pizza boxes, these thrust sheets being stacked one on another, San Juan Islands, and so on, and coming into approaching the foothills of the Cascades. But to me, that's different than when and how we're actually mixing up the melange
Yep.
to make the material. And where
It
am
gets
I imagining that mixing to happen? Is that mixing happening out in the ocean? Is it happening at the edge of the continent? Is it happening with some lateral strike slip motion? Who's doing all that mixing and when?
if we look at the detritus, if we just think about the sedimentary rocks, which are very
Yeah.
important, the sedimentary rocks are derived from older rocks, right? And so if we just look at the ages of the sedimentary rocks again, so these are detrital zircons from sandstone.
Mm-hmm.
Um, these two down here are Jurassic,
Okay.
and they have essentially no older zircons in them. They're very little um, Paleozoic zircons in them to no Paleozoic zircons in them, and no Precambrian zircons. Precambrian zircons are going to come from continental North America. These are
Yes.
island arcs, like the Lesser Antilles or like Fiji and Tonga and the Marianas Islands, right? These are island arcs that are forming off of somewhere out in an ocean basin during the Jurassic. Probably not too far removed from a continent, but they're island arcs. Their petrography suggests they're volcaniclastic, which is fancy talk for the little broken pieces of sand were derived from a volcano. Their geochemistry suggests they came from a mafic igneous source, and their point count said they come from a pretty normal looking island arc type volcano.
Mm-hmm.
This starts to change as we get younger. We start to get Precambrian zircons in them, and we start to get a lot more Paleozoic zircons in the samples. So we're tapping into the North American craton. So, so some of the sandstones in the Western Melange Belt, the oldest ones, the Jurassic ones, form in island arc settings somewhere out in a paleo ocean off the coast of modern North America. And as we get younger, we're getting a stronger connection to the North American craton because we're deriving zircons like a 3.3 billion year old zircon from the oldest parts of Canada into
Mm-hmm.
the sedimentary basin. So the answer really is both. We have sandstones that are forming along the continental margin. We have sandstones that are forming out in an ocean basin. Sometime between the Jurassic and the Cretaceous, they meet structurally, they get faulted together, and then together, I can hear my New York accent, together, they migrate from the south towards the north and meet up in Washington State and form the Western Melange Belt. So there's sandstones forming in island arc settings somewhere off the coast of North America during the Jurassic. There's sandstones forming in arc settings, still pretty intermediate to mafic arc settings, but they could easily be continental arcs because they are arcosic sandstones, and their detrital zircons have a lot of Precambrian zircons in them, some as old as 3.3 billion years old. And so they're tapped into the craton. So there could be arc proximal, like a trench deposit right off the coast, with sandstones coming in. Then everything lithifies into a rock. Then somehow they meet structurally. Then together they move to the north into Washington State.
Beautiful. I got one more. I lied. I got one more.
That's okay.
Um, so I'm imagining, maybe too simplistically, that the Granite Falls stock, that magma is coming up through a melange belt that's already there, similar to the index pluton is coming up through, like it's invading a portion of the fruitcake that's this melange belt.
And the index comes up through the eastern Melange belt, which is
Okay.
older Melange and slightly higher metamorphic grade with more ultramafic rocks in it.
But my question is, Hicks Butte, the Indian Creek in Rimrock, is it the same thing? Are
It,
those Jurassic magmas coming up through a melange that's already there?
they can't for a couple. The answer is no, and
Okay.
probably the answer is no, probably because they're faulted against each other. The
Okay.
Indian Creek complex is 154 million years old, and it's faulted against Cretaceous metasedimentary rocks that
Yeah.
are tens of millions of years younger. And
Yeah.
so they're
Yeah.
just faulted next to each other. There are
Okay.
Jurassic sedimentary rocks in there too, but the Jurassic sedimentary rocks are probably about the same age, so
Huh.
they intrude through each other. There's no intrusive contact or relationship between them. Like when you like the Quartz Mountain stock, you can go up to the top of Quartz Mountain and you can see how the stock intrudes the sedimentary rocks, the Lookout Mountain Formation, and you can see that clear relationship. And then
Hmm.
the age of the sedimentary rocks, or in the late 160s, like 162, 161, and then the stock is 157. So the stock's younger than the rocks it intrudes,
Huh.
right? Principle of cross-cutting relationships. And
Right.
so the Indian Creek complex is faulted against those metasedimentary rocks, and many of them are younger than the Indian Creek complex. So they probably didn't intrude up through them, like the Granite Falls stock,
Yeah.
or like the Grotto Index or Snoqualmie.
Jamie, beautiful job today. Anything else you wanted to add before we wrap up here?
You know, I, I'm very curious about the basement. And there, Paul Umhofer, before he tragically passed away, he started looking at some old oil well logs where they feel like they had drilled into Eocene sedimentary rocks in southern Washington, northern Oregon area. And he felt like they were the Chuckanuk or Swak equivalents, right? And so these same or similar rocks that we see that people like Mike Eddy and Stacia Gordon and Bob Miller have been working on. And these Eocene sedimentary rocks like the chumsticks and the chuckanucks, I love saying these words, and the swak, they're all hiding down there underneath the cover sequence that are now like the Columbia River basalts and all these volcanic deposits that have been deposited since the arc has established, the Cascade, modern Cascade arc has established. Also mixed in with all of that is the fruitcake,
Yes.
is these Mesozoic, Jurassic, Cretaceous terrains that are all sort of hodgepodge together. And then also, most likely off to the west is everyone's favorite. Silex is out there. Silesia is out there too, right? Because you can trace it all the way down from the north to the south, right?
Yeah.
And so there's all sorts of really interesting things going on in the basement. What we need is a good geophysicist like Megan Anderson to come along and help us out and show us using the magic of physics to sort of look down beneath this cover sequence and give us a good inference about what may or may not be down there. And if we could get geophysical data down there, we might be able to, with certainty, start to do things like extend the Straight Creek Fault from the north to the south because you can see differences in the geophysics of rocks on what would be either side of the fault and things like that. So there's lots of different ways we can answer this question. We just need really good people to work on.
And we've got some, and we're hoping to get some more. Jamie, thank you for your time today. Please hold the line. I want to talk to you after I stop the recording, but thank you so much for your time today. Beautiful job.
It's my pleasure. Anytime.
All right. Thank you.